All right, let's talk about one of the coolest ideas in chemistry, orbital hybridization. So, it all starts with a mystery. Take methane, CH4. We know it has 4 identical bonds.
But here's the thing. Carbon's electrons are in orbitals with totally different shapes and energies. So how does that work?
Clearly, our basic model is missing something. We need a new way to think about this. And way back in 1931, the brilliant chemist Linus Pauling came up with the answer. He called it hybridization. Basically, an atom just mixes its own orbitals to make new, identical ones.
Think of it like this. First, an electron gets a little boost. Then the orbitals get blended together. And what you get are these new hybrid orbitals, perfect for making stronger, more stable bonds.
So let's check out the 3 most common ways this happens. First up, we've got sp3. This is a mix of 1 s and 3 p orbitals.
And boom, you get 4 identical orbitals, making that perfect tetrahedral shape we see in methane.
Okay, next is sp2. This time, we're mixing 1 s orbital with 2 p orbitals. That gives us 3 new orbitals, all lying flat on a plane. We call this trigonal planar. And last but not least, sp hybridization. Here, it's just 1 s and 1 p orbital.
This leaves you with 2 orbitals pointing away from each other, making the molecule a straight line.
So you see the pattern, right? The type of mix directly creates a specific, predictable shape. Okay, so what? Why does any of this mixing and shaping even matter?
Because a molecule's 3D shape, well, it determines pretty much everything about it.
I mean everything, from its boiling point and how it reacts, to its role in our bodies, and even its smell.
Yup, hybridization is the key to understanding why molecules have the shapes they do and why they behave the way they do. It really makes you wonder, if atoms can bend their own rules for stability, what else in nature is that adaptable?